Okay, now we're going to move on to work, force, and energy, which is lesson number 7. Things are a little bit different here now. We've been looking so far basically at, we've looked at speed, acceleration, speed, velocity, and acceleration. And that's kind of quantifying how fast and in what direction we're moving. Now we're going to change gears into force, work, force, and energy, and how they all come together. So like I said here, you have force, work, energy. There's also plenty of calculations here. And this is going to be where a little bit of algebra is going to come in, and significant digits and units. So we're going to want to pay attention here to what we're doing, and also on the other side of this, want to attempt some practice questions. All right, what is a force? A force is is when you push or pull on an object. A force is measured in newtons, okay? This is in kilograms per meters per second squared. Now, luckily, in our course, we don't have to write. So let's say we had a force of 2.5. We don't have to go kilograms per meters per second squared. Luckily, when we have a force, we can simply put N for newtons. Now, basically, here you can read about unbalanced forces, okay? And it's basically telling you about when you apply a force to an object, why does it move? Why does it speed up? What about the direction, okay? I'd like you to have a quick read of this right here, so you may want to pause the video. This again kind of shows you about forces in diagrams, okay? When you have equal and opposing forces, in this case here in B, you have one force is stronger than the other. Here you have unbalanced forces again. I'd like you on your own time here to pause the video and have a read on that. And this will help you try to understand what a force is and why it causes things to move, speed up, slow down, etc. Now, this is how you would calculate force. Force is mass times acceleration, okay? So what I did is I made a kind of just some fake values here. A mass of 94.25 kilograms, acceleration of 25.3 meters per second square, the movement's to the east, because force is a vector. So if someone said to you, I want you to calculate, well, how strong or weak is that force? Well, what you have to do is you have to go mass and times it by the acceleration, okay? So I did this here, I put them in, so this is going to show you the proper way of calculating force. You have your kilograms, your mass, you have your acceleration. It does give you this big ugly number here in newtons. Now, based on the values you were given, we're allowed to have 3 sig digs. And as we covered a long time ago in the course, you're going to have to use scientific notation in this case to change from this value into this value. Now your final answer is going to be for this force 2.39. Oh, I put that 3 in the wrong place. 2.39 times 10 to the 3 newtons in the east direction. This is just a very simple, straightforward way of calculating force in the proper way, using a formula, using units, and using significant digits. Now, we learn about force, and then we get to move on to work. Work is done whenever a force moves an object through a distance. So the formula for work is very, very simple. Work equals force times distance. If I break this down even furthermore, remember, force is measured in newtons, and distance will be measured in meters. And when you multiply those together, you will get some number, let's just say 100. The unit for work is in J for joules. Okay? Remember though, work is done when a force moves an object through a distance. It must move an object through the distance. So here is a sample calculation. I pretended that we had a force of 2.9 newtons. We have a distance of 5.0 meters. I multiplied those together, it's 14.5. Now, if I really follow everything, these are the ugly units, but please remember, you can save yourself time. When you multiply a force by meters, by a distance, the simple unit jumps right down to joules. 14.5 joules. And again, I did significant digits. I had to round to 15 joules, plain and simple. I did want to show you one trick here, though, and this comes up from time to time. Now, over here, what I've shown you is you have work equals force times distance. Please remember what force is. Force is mass times acceleration. So there is the odd time where you will have to, you'll be at this point here, and you're going to have to say, wow, what am I trying to look for here? And you're going to have to switch force into mass times acceleration times distance. So as an example, if I just erase this here, I'll go back to kind of the start. So this is for the trick situation. Let's pretend that a question gave you these values. Your work is 20 joules. I'm just making this up very, very quick. Your distance or displacement, is, I don't know, we'll put 5 meters, okay? And your acceleration is 0.5 meters per second squared, and they want to know what the mass is. Well, if you take the general formula, there is no mass. I mean, if you look right here, I don't see mass anywhere. But what you're going to have to do then is take that formula and remember that that force can be separated into mass times acceleration times displacement. You could sub in your values now. 20 joules equals, there's m that we want to find. Our acceleration is 0.5 meters per second squared, and our displacement is 5 meters. Whoops. And you can go from there and solve the question, and you'll solve that into kilograms. My point to you is, that's a hint that I want to give you. Sometimes you're going to have to break, within the work formula, you're going to have to break the force into mass times acceleration. Okay, so these are the conditions of work. Please don't get caught. Sometimes on an exam or a quiz, they're going to try to catch you up on this. And that is the conditions for work. There has to be a movement. There has to be a force. And the force and the distance must be in the same direction. If those conditions are not met, you do not have any work being done. This one is pretty standard. You have someone pushing against the wall with 100 newtons of force. But the wall isn't moving. So, think of this, I often think of this as people in the middle of winter trying to push a stuck car. They might be pushing on, let's say, the bumper side of the car, and they could be sweating and hot and tired. They're putting a lot of force into it, but it's not moving. So are they doing any work? Well, if you take a look at, if I do this mathematically, our force in this case is 100 newtons. But what's the displacement? Has this wall moved? Well, no. So even mathematically speaking here, our answer is 0. We have done no work. So next time you see someone pushing a car stuck in the ditch or stuck in the snow, and they've been pushing for, let's say, 20 minutes, and they say, I did a lot of work. Well, but if the car didn't move, they actually did no work. They put in an effort force, but nothing happened. So there was no work. The second category is when you have, let's say, you're going over a distance, but you have no force. So in this situation, the person is riding the bike, but they're gliding. So let's just pretend that the bike in this case moves, I don't know, we'll say 25 meters. But for the last 25 meters, the person has been gliding. They have not been applying any force to the pedals. Again, in this case, your force is 0 newtons. So even mathematically here, we have 0 joules, which means no work completed. The final example is, this one's a little bit trickier, but if you look here, the force and the distance the object travels must be in the same direction. So you look here, a person's carrying a backpack, holding it, but they're moving. So the force to hold the backpack is vertical. They're holding it up. But the direction of walk, of travel, is to the side or to the right. This breaks the one rule. The force and the distance traveled must be in the same direction. In this case, the force is up and down. The direction is left and right or horizontal. So we have 0 joules of work done, no work. Okay. Please do your best to remember those 3 conditions that are required for work. These are just some basic examples here from your textbook. The first example is B1.11. They give us a displacement of 2.4 meters. They give us a force. I just wanted to show you quite simply how this could be calculated. So you do have to put in, so you have your blank formula, then you should sub in what you have, so 2.00 times 10 to the 3 newtons. You can use brackets if you like. And your displacement was 2.40 meters. So in this case, what we're going to get is going to be, pardon me, sorry. And that's going to be times 2.4. You get an answer of 480, so 4,800 joules. Of course, I'm not in proper significant digits for this because that has 4. I need to be down to 3. So it's going to move, decimal is going to move there. So it's going to be 4.80 times 10 to the 3 joules. Fairly simple and straightforward answer there. The other question I wanted to show you here is where they want you to solve for force. And we know that work equals force times distance. I want to show you 2 ways of doing this. The first type is, so type 1, so work equals force times distance. Your work is 2.2 times 10 to the 4 joules equals force times 9.5 meters. Now, if you remember back to the algebra lesson, we use bed mass backwards and opposite. Well, I need to get this force by itself. It's being multiplied by 9.5. So with algebra, we always do the opposite. So if I want to get force by itself, I'm going to divide out the 9.5 meters, divide out the 9.5 meters, and what we'll get here, just allow me to do the calculation, 2.2 times 10 to the exponent 4, and we're going to divide that by 9.5. Whoops, sorry, my calculator just giving me some issues here. With correct significant digits, it's going to be 2.3 times 10 to the 3 newtons. Okay, no big deal. I'm not really worried here about the math. I'm really worried about the type of algebra. You might remember, though, the other way of doing this was manipulating the formula in the first place. You see, what I did here, guys, is I gave you the blank formula. I put in my numbers and did algebra. Another way of doing this, if I can just kind of give us some space here, if you want to try type 2, some people really enjoy this way a lot more. It's where you manipulate the formula ahead of time. So this is type 2. So you have work equals force times distance. Now, this question, they want you to get force by itself. Now, you can see the force and the distance are multiplied by each other. So what you could do, if they're multiplied, the opposite is divide. You could divide this side by d and divide this side by d. That now gives you force is equal to W over d. And then what you would do, of course, is you'd fill in your values. So you go 2.2 times 10 to the 4 joules divided by 9.5 meters equals force, and you can go from there. I suppose what I'm trying to say to you is either you can use algebra whatever way you want. You can start with a blank formula, input your numbers, and solve. Some people prefer to take the blank formula and isolate the variable or the letter on its own and then input the values. It doesn't matter. You may want to look at this this slide again. But anyway, I hope at this point in time the algebra isn't causing you any grief. I also hope that using scientific notation is working out okay for you as well. The final part of this lesson is energy. This has come up a few times in some questions, and some people have been kind of lost what to do here. I just want you to know, if a body has energy, then the body can do work by transferring the energy to another object. So just so you know, basically, the best way to actually explain this is probably going to be with the example. So, energy is the ability to do work. We have work equals energy, et cetera, et cetera. Perhaps more, like I said, this is going to be easier to understand if we look at the example. The example on page 160b.12 says you have a weightlifter, and this person does 4.8 times 10 to the 3 joules of work. How much energy is gained by the barbell? Well, so the weightlifter did work, and the formula says that's equal to the change in energy. I just reversed up here, as you can see. Now, the weightlifter, it says right there, did 4.80 times 10 to the 3 joules of work. Now, think of it. This person did work on the barbell. To lift that barbell required all that energy. So now when that barbell is in the air, that barbell now has that exact same amount of energy. Okay? So again, if I put in another context, let's pretend your cell phone's on the ground, and you do, let's just say, 10 joules of work to pick it up. Well, now that phone is in the air, it has gained 10 joules of energy. So please be aware of this little tricky, it's not a tricky formula, it's very easy, obviously, but it's something that sneaks up from time to time. And the key here is to remember, if you do work on an object to lift it, that object has gained that amount of energy. Finally here, everybody, we have looked at force, we have looked at work, we have looked at energy. I wouldn't say they're the most difficult formulas. I would say there's probably a lot to remember. I would say that it's important to be able to calculate and use those formulas in the proper way with significant digits. I am going to give you some practice here, and it's also important, please, to rewatch this video or read the pages in textbook. We're going to move on. The next sections now get a little more intense with some of the calculations, but please make sure you have a solid grasp of concepts of force, work, and energy before you move on.